about this last week, how you look at these differences in electronegativity. Oh, sorry, I didn't. We talked about these differences in electronegativity that lead to polar bonds, and then we can look at the molecule as a whole, and if we know its shape, we can determine whether that whole molecule will be considered polar or not. So we're going to do that here. Nitrogen trifluoride, the first one. Really, we should really look at the right two first before we decide if the molecule overall is polar or not. So would you say that that contains polar bonds or non-polar bonds, or both? What do you think? Polar? Why polar? Yeah, they're two different things, and there's a significant difference in their electronegativities. Nitrogen is 3.0 and fluorine is 4.0, so there's a difference of 1. And we said any difference greater than 0.4 or so we consider to be polar. So yes, we would say that this contains polar bonds. Does it also contain non-polar bonds? Probably not, right? Because it only has one type of bond, NF bonds. So that's probably all that's there. All right, what about the overall molecule then? Is the molecule polar or is it non-polar? How do we determine that? It is polar. How do you know? Right, that we can say that there's two sides. Remember, polar means two poles or separated. We can say there's a more positive side up here and a more negative side down here. So we can say that that is probably a polar molecule. You've got a pyramidal type shape, like a pyramid, and the bottom part is more negative and the top part is more positive based on how those electrons get distributed. All right, good. What about this next molecule, formaldehyde? Would you say there's a polar bonds there? Non-polar? Non-polar? This one actually has both. The carbon-hydrogen bonds are non-polar, but the carbon-oxygen bond is polar. So in this case, because there's a difference between carbon and oxygen in electronegativity, so the electrons are pulled more toward the oxygen, but between carbon and hydrogen, there's no real difference. The difference is really small, 0.4, so we say that's essentially non-polar. So that actually has both types. Now, overall, is the molecule polar or non-polar? We look at the same idea. Is there going to be more of a negative side where the electrons are pulled and a positive side where they're pulled away from? Or is it all kind of evenly distributed around the molecule? This one, yeah, this one is going to be, again, polar. If we kind of cut this, we would see that we have an area where the electrons are going to get pulled, which is toward the oxygen. And then the other side, they're not. Right? The other side they're being pulled away from, leaving some positive area. So once again, we have a negative area and a positive area. As we talked about in class, the main indicators, if you're looking for, if something has polar bonds in it, but it's going to be overall non-polar, it has to be very symmetric. It has to have like everything around the center in the same way. We looked at carbon dioxide as one. We looked at some tetrahedral type compounds, sulfur trioxide, if you go back and check those out in the notes. And so you see there's like a symmetry where all the stuff is around and you can't say, all right, we're going to cut the molecule and this side is positive and this side is negative. So we won't be able to say that. So then what about the last one, nitrogen, N2? Yeah, that one's going to be non-polar with a non-polar bond between N and N. If it's just N and N, there's no difference in electronegativity there. So there's not going to be, the electrons aren't going to be pulled more to one side or the other. They're going to be evenly distributed. Okay, so back to some naming. As I've said, naming doesn't disappear. There's going to be an issue in everything we do for the rest of the semester. So you got to make sure that you can do these kinds of things. And you'll see why today when we start looking at some different chemical equations. So tin carbonate, tin 2 carbonate tells us that we have a 2 plus SN. And then what's carbonate? CO3 2 minus, right? So we've got 2 plus from tin, the 2 minus for carbonate. So the overall formula is just SnCO3. Okay. PF5, got to come up with a name for this one. Is this going to be a ionic or covalent compound? Yeah, this one's covalent because phosphorus and sulfur are both nonmetals. They're both over to the right. So how do we name covalent compounds? Right. We use that prefix, and this is going to be phosphorus pentafluoride. If it's not ionic, we need to specify exactly how many of each thing there are, because there could be different ones. And then finally, magnesium nitride. Magnesium we said was Mg2 plus, and nitride is N minus 3. So if we want to get a 2 plus and a 3 minus to balance out to 0, we have to go Mg3 N2. And that's a formula of magnesium nitride. And finally, what is the major type of attractive force that occurs between iodine molecules? What is that? Remember the different attractive forces? We've got dipole forces, ionic forces, dispersion forces, and hydrogen bonding. So you say dispersion forces for this one? Maybe? Yes? Well, I thought I heard somebody say dispersion forces. So definitely go back and see what types of molecules those types of forces go with. Iodine, is that more a polar or non-polar molecule? No. Or both? That's non-polar. That's the same thing. So what are the only types of forces that non-polar compounds can have? The dispersion forces. Yeah. Yeah, the dispersion forces, the ones, those what we also called induced dipole forces, the ones where they're not actually polar, there's no positive and negative areas, but momentarily some of the electrons can rearrange themselves and align in this way that allows them to kind of stick together. We talked about non-polar things like gasoline and then waxes that are totally non-polar but still stick together because of these dispersion forces. The polar compounds can have those other types of attractive forces, hydrogen bonding, dipole forces, and ionic forces. So, yes?
Can you go over like the polar and non-polar again?
Yes.
Like, how do you determine whether a molecule is polar and non-polar? Just from the chart?
Sort of. Let's go through it again. So let's go through more specifically with these. So to determine whether a molecule is polar or non-polar, like with formaldehyde here, you first have to look at the individual bonds and decide if the individual bonds are polar or non-polar. In this case, carbon-hydrogen is non-polar because there's not a big enough difference in the electronegativities, which are given in the table there. But carbon-oxygen is polar because of the larger difference in electronegativity. So we can say that in this carbon-oxygen bond, there's going to be a more negative side and a more positive side. If we go up to this nitrogen trifluoride, same thing. We look at each nitrogen-fluorine bond. Those are definitely polar. So for each of those bonds, we can say there's a partial positive and a partial negative separation there, where the electrons get pulled more to one than the other because of the greater electronegativity. Now, after we've analyzed each bond like that, we look at how that contributes to the overall molecule based on its shape. Does that make the overall molecule have kind of a lopsided arrangement where there's more of a positive over in one part and more of a negative over on another part? And in both of these cases, that's true. In the nitrogen trifluoride, because it's kind of a raised pyramid type structure, the positives are all kind of near the top and the negatives are all kind of near the bottom with the fluorine. So there's definitely two poles to that molecule, and that's what polar is. There's this positive pole and a negative pole. So we would call that a polar molecule. Same thing with formaldehyde. You have the positives kind of concentrated down toward the bottom of the molecule and the negatives up at the top of that oxygen. So we have a separation there in charge and a difference in charge, and therefore that molecule is overall polar. Now that upper one, that nitrogen trifluoride, if that were not a three-dimensional pyramid type structure, but rather a flat structure like this, then it would actually be nonpolar, because the positives would be concentrated in the middle with the negatives on the outside, and that would kind of all cancel each other out. All the different polar bonds would cancel each other out, and you'd end up with nothing overall. So the fact that it's introduced asymmetry or unevenness by pulling that nitrogen out of the plane gives us a positive section and a negative section. And that's how we know that it's polar. Yeah.
So say for formaldehyde, if you have these on top, would that be nonpolar?
Right. Or if it were oxygens all around, also it would be nonpolar. Yeah.
Which one again is forces?
Yeah, let me pull up the notes from before so I can see them all. There we go. So these different types of intermolecular, or attractive forces. We've got the dipole-dipole forces, which are these positive, negative forces between dipoles. When you have polar bonds, you can have polar forces. Then you have the extra strong ones called hydrogen bonding, which is if you have NH-OH or FH bonds. And then the nonpolar forces, which are these dispersion forces that happen when you have nonpolar molecules, but they can still have these temporary slight dipoles, which is the polar part where they're got a little bit of positive and negative. So that happens temporarily and leads to a slightly attractive force. The other force that's not here is what we call ionic forces, which is just ionic bonds, the really strong ones between ions like MgF2 or NaCl. Other questions about this? All right. Yeah.
How do we know for nitrite that it's
The 3 minus?
3 minus?
Yeah.
I put 5 minus.
Right. So it's in the 5th group, which means that it has 5 valence electrons and wants to get to 8. So it could either lose 5 electrons and become 5 plus, or it could gain 3 electrons and become 3 minus. And whenever there's that choice, we usually go with the smaller number. So 3 minus takes fewer electrons to deal with than 5 plus. There's another reason also. This is paired up with a metal, and we know that metals always take positive charges. So nitrogen is not likely to lose 5 electrons and also be positive charge, so we have to go with the 3 minus instead. There are actually compounds like the nitrate ion where we say that nitrogen is more of a 5 plus state.
Dioxide.
Yeah, that NO, like nitrogen with oxygen sometimes has that.
Dioxides.
Yeah, but with nitrogen paired up with metals will always be more negative.
Okay.
Other questions? All right, we'll have a 4th quiz next Tuesday on the balancing chemical reactions and moles and chemical quantities, that kind of stuff that we finished talking about this week. All right. So lab today, we actually get to do some reactions, a lot of burning stuff, a lot of color changes. It should be a good one. Hopefully nobody gets hurt. It's always the hope. I'm sure you'll be fine. But last time we ended, we talked about some types of reactions. There's one more type that I want to talk about, and then we're going to practice classifying these reactions in their different types because there's some practice with that in the lab also. Then if there's still time, we'll get into the chemical calculations, so how we determine how much of a particular thing we might need in a reaction. All right, so we talked about these different categories: combination, decomposition, single and double replacement, all of which we're going to do in lab today. And the last category, it's what was my number on here? 2, 3, so this would be 4. Is combustion reactions. What do you think combustion means? Have you heard that word before? What does it refer to? Burning, flames, yeah. Yeah, so we use it kind of in everyday life to just refer to burning things, blowing things up, that kind of stuff. But it has a very specific chemical definition, which is a hydrocarbon, something made of carbon and hydrogen, reacting with oxygen. And these reactions always produce carbon dioxide and water. So what you're looking for to determine if a reaction is a combustion reaction, you're looking for something with a lot of carbon, hydrogen, or oxygen. It could have some other stuff too, but it should pretty much just be carbon, hydrogen, and oxygen. Reacts with molecular oxygen, O2. And then the products are always carbon dioxide and water. So that's pretty easy. You don't ever have to try to figure out what the products are going to be. As soon as you can tell that it's a combustion reaction, you know the products are going to be carbon dioxide and water. Is this equation balanced? How would you balance it? Yeah, we need 2 here and then 2 here. I think that'll do it. All right. So now we've got these 4 categories of reactions. Sure. We could look at all kinds of different ones. Let's look at methanol. So methanol is CH3OH. That could also combust. We're going to have to balance this one a little bit differently. Yeah, but the same idea. So something with carbon and hydrogen and oxygen plus oxygen. And this is what happens when you burn hydrocarbons. When you burn anything with carbon, hydrogen, oxygen, that could be things like gasoline that are hydrocarbons. That could be things like wood that are made of carbon, hydrogen, and oxygen. If they burn completely in oxygen, you should only have carbon dioxide and water left. Now, in your experience of burning things, which I assume is pretty vast, and probably burned a lot of stuff in your times, is your experience that when you burn something, there is nothing left behind? What's usually left behind? Ash. So that's an indication that this reaction usually doesn't fully go to completion. And the reason for that is there's usually not enough oxygen around to fully combust everything. We have an instrument in the lab called a bomb calorimeter. It's a big steel thing, and we can put stuff inside it and charge it with pressurized oxygen and then combust it. And when you open it up, there's nothing left. It's all turned into carbon dioxide and water. And things like in the Bunsen burners, you can try this yourself sometime. If you want a really efficient burn in those Bunsen burners, what do? You open those windows up, and it gets lots of oxygen in, and it gets super hot and super purple because it's being really efficient burning everything. And that flame's very clean. When you heat a beaker with it, you don't see any ash or soot or anything. You're burning that natural gas really cleanly. If you close those windows up so it has that big kind of yellowish flame that kind of flickers around, you know what I'm talking about when that happens? If you try to heat a beaker with that, the bottom of the beaker will get all black from soot, from incomplete combustion. So complete combustion actually should leave nothing behind. But usually what we experience is incomplete combustion, where we're also making some other byproducts. Other byproducts of combustion. So if we, again, combust something completely cleanly, carbon dioxide and water are not harmful. But often one of the byproducts of incomplete combustion is carbon monoxide, which is harmful and is poisonous. So that's why you're never supposed to burn grills indoors or have open fires indoors, that kind of thing. Okay, so now we've got these different categories. Now let's practice categorizing some of these reactions. So I'm going to pull in this one from the book. I guess that's as big as I can get it. I want you to look at each of these and classify them as one or the other. If you don't have notes from last time, you can pull them up on your phone from Blackboard or take a look in the book. The categories are also there. See what you come up with. I'll go to the bathroom. I'll be right back. All right, you got some categories written down? All right, what'd you come up with? A. Double replacement? How do you figure? They switched. Yeah, they switched. So this copper went with the chloride, the hydrogen went with the oxygen. And yeah, notice with that one, the ratios change. So it's not as simple as simply pulling the letters apart and sticking them with their new partners. You have to adjust the ratios based on the charges. Copper is 2+, oxygen is 2-. So when a 2+ copper goes with a 1- chloride, it needs 2 of them. Similarly, when a 1+ hydrogen goes with a 2- oxygen, you need 2 of them, so it's H2O. So make sure that you readjust those, and we'll practice that in a minute of actually coming up with the new product. What about B? What's B? Combination, yeah. And C? Combustion. D? Single replacement. And then E? That's going to be a decomposition, right? See that one breaking apart. Good. So categorizing those is the first step to what we really want to do, which is predicting the reactions. If we can categorize these, then we can have a good chance of predicting what products will be for reactions that we might not know. All right, so let me see, grab my stuff here. So one thing I might ask you to do is to write a balanced equation for the following things. So first, molecular chlorine reacts with sodium bromide. Now, notice what's missing here. Of course, formulas aren't given, but we can do that. But more importantly, the products aren't given. It only says that these two things react together. So we have to figure out how to predict the products. The way we're going to do that is first we're going to come up with the formulas so we can look at it symbolically, then determine which category it fits in, and then make a prediction of how it might react. Now, we might not be right because there's all kinds of chemical reactions and you can't always predict them, but we could probably make a good guess at what the product should be. So what's the formula for molecular chlorine? Chlorine by itself is an element. What's that formula?
CL2.
Cl2. Right, we've got to remember that there are those diatomic elements, the ones that always take a 2. H, N, O, F, Cl, Bri, always take a 2. Always form a molecule. So that's our molecular chlorine. And then what's the formula for sodium bromide? NaBr. Right, very good. Okay. Now, what kind of reaction does this look like? Where would you categorize it only seeing one side of it? Probably a single replacement. Does everybody see that? You've got one element by itself, and then one ionic compound, one pair. So that means that we're going to rearrange it in some way so that one of those elements from the NaBr ends up by itself, and the chlorine goes with one of the Na or Br. Now, we got a couple choices there. The chlorine could go with the bromine, and the sodium could be by itself, or the chlorine could go with the sodium, and the bromine goes by itself. What do you think? Why? Yeah, so it's going to keep that same idea. So the sodium can go with the chloride, and the bromine ends up by itself. Now, do we know that for sure when we look at a problem like this? No. Could it be possible that the sodium ends up by itself and the chlorine ends up with the bromine? Yeah, I guess it's possible. This is a better guess for a couple reasons. One, it keeps the same form. You'll notice in the single replacement type reactions, usually you've got nonmetal and then metal nonmetal, and then your product is going to keep that same form. So the metal nonmetal stay together and the nonmetal goes by itself. Sometimes it's the opposite, like the one you're going to do in lab today, which is these types. Oops, that's still a replacement. These types up here. You've got metal, and then the H with the Cl. Then the H, what was the positive ion goes off by itself, and this becomes positive with the negative chlorine. So it kind of keeps the same format. It would be unlikely that it would go zinc with the H and then the Cl by itself on the other side. And also some of this is using your chemical intuition. Even though you haven't been in chemistry for very long, a lot of you probably already realize that sodium chloride is kind of a thing. It's around a lot. You know, it's a pretty common substance. So if you make sodium chloride, yeah, it's probably more likely than ClBr, which is something maybe we haven't seen before, which actually does exist, but not as obvious. All right, is this balanced? It's not. So we got to balance it. And get something like that. All right, let's try another one. Potassium sulfide reacts with lead-2 nitrate. Same idea. You're given the reactants in words, so you have to write down the formulas, determine what category it falls into, and then write the products based on what's predicted by that category. So see if you can do this whole thing yourself and come up with a balanced equation from those words. Because we don't have the periodic tables with us, potassium is what symbol? K, and sulfide is S, and then lead is Pb, and nitrate is one of those polyatomic ions. What's its formula? NO3 and -1. All right, you come up with a balanced equation? Think so? Maybe? Maybe not. Let's look at our reactants. What'd you get for potassium sulfide? One's going to be K2S, because we know potassium's +1, sulfide's -2. And then what about lead-2 nitrate? Right, we've got a 2+ lead and a 1- nitrate. So we need 2 of the nitrates to balance out the lead. Okay, but what type of reaction does this look like to you? Why double replacement? Yeah, so you've got 2 kind of ionic pairs, right? 2 ionic compounds, each with a positive and negative ion. And so they're going to switch partners, but we have to remember here, when they switch, we may have to come up with new ratios. We can't just say the K2 goes with the NO3 and the S goes with the Pb. It might not work out that way. We have to think about the charges and figure out how they're actually going to do that. And one of the ways to do that is actually use the words. So if we've got potassium sulfide reacting with lead nitrate, and we know it's a double replacement, it's actually easier to switch the words first, because then you don't have to worry about those ratios. So you can say potassium goes with nitrate, and then lead-2 goes with sulfide. So then you can build those new compounds once you've switched them. Potassium nitrate is KNO3, and lead-2 sulfide is PbS. So we need to put a 2 here to balance it, and then we've got our balanced equation. All right, look good so far? So as you can see, you still need to know those names. You need to be able to write those formulas from names. So please go back and review that if you need to. Balancing equations, also really important. And we're going to look at this next part we're going to go into. Not only do you have to have your formulas right, but you have to have the equation balanced properly so that this next part works. So the next part is chemical quantities. That is, how much do we have, or how much do we need? And the fancy word for this is stoichiometry, but it just means how much do we have and how much do we need. So the goal of this, you're doing a chemical reaction in the lab. Imagine you want to make something. You want to make, well, let's say we were doing this previous reaction that we just looked at. We're doing this reaction because we want to form lead sulfide. We want to make some lead sulfide to give to our friends as presents. Well, let's say, don't give your friends lead sulfide. This is a crappy present. You know, poisonous, and it's just a rock. But anyway, let's say we wanted to make lead sulfide. We'd want to know how much to make. So let's say we want to make 10 grams of lead sulfide. That's our goal. Well, we need to know how much potassium sulfide do we need and how much lead nitrate do we need. How do we figure that out? How would they react in such a way to give us the amount of lead sulfide that we need? And this is what this part is going to tell us about. So we're going to look at a slightly simpler reaction just because it'll make things a little easier to look at. We're going to look at the reaction between silver and sulfur to make silver sulfide. Here's the balanced equation. Silver, regular elemental silver, reacts with sulfur to form this compound silver sulfide. Now the balanced equation, we've been doing this kind of abstractly lately, in that we've been kind of just talking about how to put the numbers here and how to put the numbers there. But let's think back to what that really means. It means that for this reaction to happen, you need 2 atoms of silver and 1 atom of sulfur. And they need to be in that ratio, or they're not going to react properly. Remember the thing about the hydrogen and oxygen, and we couldn't make one of them just disappear. We had to kind of keep all that together. Same idea here. We need to have 2 silver atoms react with 1 sulfur atom to make this compound of silver and sulfur. It's just a diagram, but you get the idea. They have to be in that ratio. You can't just have one of these and one of these. So this tells us that depending on how much we want, we can calculate this. We're going to make a little table. If we have a certain amount of silver, we need a certain amount of sulfur, and then we make a certain amount of silver sulfide. So the way we just drew it, if we have 2 atoms of silver, we need 1 atom of sulfur, and then we make 1, it's not really a molecule, but we'll put it in quote, 1 compound or something of Ag2S, or 1 of those. Now, usually when we do reactions, we're not counting individual atoms because they're too small. So what do we count instead when we do reactions? Well, we'll measure by mass, yeah, and we'll get to that probably on Thursday. But we're going to count in moles of atoms, which is this huge number of atoms, and that's a reasonable amount that we can actually deal with. So if we have 2 moles of silver, how many moles of sulfur do we need? 1, because they're in the same ratio. Remember, a mole is just a count, like a dozen. So if you need 2 of these for every 1 of these, 2 moles of this, 1 mole of this, and then we'll make 1 mole of silver sulfide. But what if we don't have such nice numbers here? What if we have 1.5 moles of silver? How much sulfur would we need? Right, half of that, because they're always going to be in this 2-to-1 ratio. And then how much Ag2S would we make? We'd make 0.75 moles of this because the equation tells us that we're going to make one of these for every two of these, or one of these for every one of these. So if we have 0.75 of these, we're going to make 0.75 of these. And in fact, if you have a balanced equation and you know one thing, one quantity of from all the reagents, you can find all the other ones. I'm going to put some in here and then leave some blanks and see if you can fill in the appropriate numbers. So in each of these, we kind of got like 3 different reactions here, where only one quantity is given. Go back up to our reaction here. If you start with 3 moles of silver, how much sulfur do you need and how much Ag2S do you make? If you start with 0.33 moles of sulfur, how much silver would you need? How much Ag2S would you make? And so on. So see if you can fill in those blanks based on those same ratios that we've just been talking about. Do something like that? Okay, great. Now for the last part, what happens when these numbers aren't quite so nice? So let's look at this reaction. Instead of silver and sulfur, we're going to look at iron and sulfur. Because when iron and sulfur react, they make iron 3 sulfide. And so our balanced equation looks like this. So now if I said, if we make the same kind of table, so let's see how much iron, how much sulfur, and how much iron sulfide we make. If I said something like, well, we're going to start with 1.5 moles of sulfur, how much iron do we need? Yes, in this case, it's 1 mole. So good. And then we make half a mole of this. So maybe you can do this in your head. But if you can't, let's look at a way to do it kind of using the formulas, using it like a conversion formula. In fact, let's make an even messier version of it. So let's just come up with some random number. Let's say we have 1.234 moles of Fe. How much sulfur do we need? We can set this up just like a conversion problem. So we can say 1.234 moles of Fe times, and then we want a conversion factor that tells us how many moles of Fe per how many moles of S. That factor is the ratio that's given in the equation. So the equation tells us that there are 2 of these for every 3 of these. So we can evaluate that and find that number. There we go. 1.234 times 3 divided by 2 is 1.851. And then we could also do the same thing, find out the moles of FeS that we would use. Whoops, no, wrong spot. So we can find a conversion factor that takes us from moles of Fe and gets us to moles of Fe2S3. That's going to, again, from the equation, tells us we have 2 of these for every 1 of these. All right. Do you see how that works? Now, remember that these moles can also be thought of in terms of mass because of the stuff we did last week when we talked about how to say how many grams are in a mole for various things. So we'll stick that part on there as well. But just thinking about moles for now, let's look at a problem where these would kind of all come together. If I can get it to come on, there we go. All right. So this part of the book, because they're just looking at one thing, they give you all the balanced equations. But I want to look at one when we don't have that. Carbon disulfide and carbon monoxide are produced when carbon is heated with sulfur dioxide. And then I'm going to pull up these 2 questions that were asked about it. How many moles of carbon are needed to react with 0.5 moles of SO2, and how many moles of CO are produced when 1.2 moles of C reacts? So we need to first come up with a balanced equation, and then we can evaluate this the same way we just did in those tables. So what are our reactants? What goes on the left? Careful. Carbon disulfide is CS2, but these are not the reactants. These are produced when this is heated with this. And this is a common mistake that you always want to write down the ones that are listed first as the reactants. That's not always how it's going to be listed. So you have to look at the sentence and see what's actually happening. What's actually happening is carbon is heated with sulfur dioxide. These things then are produced. So we would say in our equation, carbon plus sulfur dioxide forms carbon disulfide and carbon monoxide. Is that balanced? Don't think so. So we should balance it, huh? Now, what do we say is in terms of a rule about balancing equations? There's really just one rule about what you start with. Anybody remember? How do you know which element to start with when you're trying to balance something? Well, it's really what not to start with. If there's any element that's in multiple compounds on the same side, you want to leave that till the end. So in this case, that's carbon, right? There's 2 carbons on the right, carbons in CS2 and CO. So we don't want to balance that one first. The reason is that because it's in multiple compounds, when we adjust anything else, we're going to throw that one off, and it's going to get messed up. So we leave that till the end, let everything else throw it off, and then work it out. So let's start with, I don't know, oxygen. We've got 2 on the left, 1 on the right, so we put a 2 here. Then we can go to sulfur. 1 on the left, 2 on the right, so we put a 2 here, but that throws off our oxygen again. So we got to take that out and rebalance the oxygen so that we've got 4. Now the sulfur, 2 on each side, and oxygen, 4 on each side. That works, right? Carbon, we've got 5 on the right. Got to make sure to add them all up from both compounds. So 4 from the CO and 1 from the CS2. So that means we need 5 over here. Now that's balanced. Okay, now that we've got the balanced equation, see if you can answer those 2 questions. How many moles of carbon are needed to react with ½ mole of SO2, and then how many moles of CO are produced when 1.2 moles of C reacts? So you're going to do the same thing that we just did with the iron and sulfur and the silver and sulfur with this new equation. You'll notice these numbers are a little bit weirder than the last one, so it's harder to just kind of look at it and figure it out. So you really want to use those equations. You really want to come up with a conversion type factor to get from one to the other. So for that first one, we can think of it as this kind of a conversion. We're going from moles of SO2 to moles of C. And to do that, we can come up with a factor that cancels out moles of SO2 and leaves us with moles of C. And that factor we get from the equation. We see that there's a 2 next to the SO2 up in the balanced equation, and a 5 there. When we calculate that, get 1.25 mole C. Same thing here, except we're going to start with moles of carbon and end up with moles of carbon monoxide. Again, the equation tells us this is going to be 5 of these for 4 of these. We've got 1.2 times 4 divided by 5.96. Right. And then, so you can see here that while this always kind of is the same way, certainly something new and something that's going to take practice. The good news is these types of questions are always the same. So once you know how to do these, just do a bunch of them and you'll be fine. And like on the quiz next week and then the exam, it'll always look the same. We will add in on Thursday, we'll add the masses to each side. But it also, you can see here why it's so important. If all you're given is that initial sentence, you have a lot of work to do before you can get to this right answer, because you have to first write down a correct balanced equation. And to get the correct balanced equation, you also need to be able to write down the correct formulas. Because if you write SO instead of SO2 or something like that, or you don't balance your charges properly in the right compound, then the equation's not going to balance properly. And if the equation doesn't balance properly, then you have the wrong mole factors for when you do your ratios down here. So the whole thing kind of depends on writing down the reagents or writing down the compounds properly, balancing the equations, and then putting in the numbers. So it's all kind of fits together. So please go back if you haven't mastered the naming and writing down compounds things and the balancing equations. It's a big part of this, and then we'll add on this other part as well. So we're just about done with chapter 7. So please make sure to make your way through that homework and work on that to be ready for the quiz on Tuesday. Other than that, I will see you up in lab and be ready to do some chemical reactions. Make sure you all got your good shoes and stuff.